Hello again. This is about task parallel programming and a particular focus on performance. A recap of task parallel programming. In a task parallel programming program, you have a thread which generates tasks by means of some kind of annotation. These tasks become part of a task dependency graph. Created tasks are put in a ready queue, conceptual ready queue. As you can see in the video about task scheduling, there can be a different kind of implementation, distributed or centralized queues, but conceptually it's a ready queue, and then you have worker threads that grab tasks from this ready queue and execute them and can generate new tasks as they execute. First of all, I'm going to present just a little bit about a world-class task parallel implementation called Wool. This is a pure C library usable with all GCC compatible compilers and really targets fine-grained. It has a really major focus on fine-grained computations. And it supports tasks and parallel for loops, and if you would like to download it, here is the web link. And you can try it on. This is how it looks like, the famous Fibonacci function expressed in Wool. You see it's very similar to the task parallel libraries that I have introduced in a previous lecture. You'd identify a function as being a task, and you can spawn new tasks, and you join the tasks. So this is similar to, for instance, C# or Java fork join, that you join this one task only and not all tasks collectively. And then you can have a call, which is a spawn immediately followed by a join. If you compare Wool with some other models, you can have a look at these graphs here. For each graph here we have from top a Wool, then we have Silk++, which is a predecessor to the current Silk+. We can have GCC's OpenMP implementation, Intel C compilers OpenMP implementation, and MCC, which is an experimental research compiler and runtime system developed by Barcelona Supercomputer Center. Here we have 5 programs: a fast Fourier transformation, the n-queens problem, a sorting application, sparse LU factorization, and Strassen matrix multiplication. Oh, I should say also, for some of these applications, we also have the Sun or Oracle C compiler implementation of OpenMP and TBB here. The point to make here is, well, what we see here is the speed up of these programs compared to sequential execution on GCC on the same processor, and this is on a machine with 8 cores and 8 workers, of course, then. And we see that all of these programs have basically, all of these applications have more or less the same behavior. There are some differentiations here. But they are really minor, right? However, the thing with these programs is that the task granularity is rather large. So, if we go to a fine-grained program, and here we've taken the n-queens as a particular example here. If we try to make the granularity of this application as with so small tasks as possible, exposing as much parallelism as possible, we see big differences in these models. First of all, we see that the Oracle Sun C compiler and the GCC compilers are particularly poor. They stop scheduling. They stop scaling at they don't even scale to 2 cores. They don't go above 1 in speed up with any time. Next, the Mercurium, the research compiler, is also not very good here in this context. The Intel OpenMP implementation is okay. The Silk++ implementation is a little bit better. And TBB is furthermore a little bit better. But only Wool in this context is producing really good result in this case. So how can we reason about performance with task parallel programming? Well, there is some theory around this. So there is a work span theory, and I'm reserving most of the effort on this to a different lecture. But I can specify that there's an upper bound on the execution time on P processors, and that is specified by the T infinite. This is the time to execute the program on an unlimited number of processors. This is also called the span. And then, so this is sort of a, it cannot, you cannot execute the code any faster than this with any number of processors. And then you have T of 1, which is the execution time of the program on one processor. This is called the critical, the work. T of 1 is called the work of the program. This is the execution time on one processor, and T of 1, the work over P, is sort of the perfect speed up of the program. So you can't execute any, this is, and you can then find out that the execution time on P processors is, if you have fulfilled certain conditions, is guaranteed to be lower than the infinite execution time, the span, plus the perfect speed up time. But you also know that you can't really execute any faster than the perfect speed up time. It assumes that we have a work stealing scheduler which is fast and in constant time. It assumes that there is a big slack, parallel slack, lots of parallelism, which means that the infinite, the span is overwhelmed by the execution time of one processor over a number of processors or cores. And also it assumes that the execution time of an instruction is independent of the scheduling. In reality, it really depends on the caches and cache computations. It assumes also that computation does not depend on scheduling, and so on and so on. This graph shows basically these limits. So here is the speed up sort of determined by this factor here. Sorry. This is the speed up limited by this factor here. And this is the speed up limited by the available parallelism in the code. With Silk, there is a program called SilkView which you can use to find out where your program are in this range here, and it will also, if you give it number of cores to test on, it will also plot your actual result somewhere in this range. So to conclude about tasks, task parallel programs are malleable. That's a very, very good property. They adapt naturally to the number of cores or threads given to them. They can deal with performance heterogeneous processors. They are composable with other task parallel programs. So all of these three properties are extremely, extremely good. So malleable means that no matter how many threads or cores you give to them, they can, as long as you have parallel slack in the code, they can deal with it. They scale gracefully. Performance heterogeneous processor means that some cores are faster than the other ones, but otherwise they execute the same kind of instruction set. That is, we don't have that such computers, you might ask yourself. Yes, you do. Even in today's computers, there is a thermal throttling. So the hardware may choose to slow down a core if it becomes too hot. So in reality, you do have performance heterogeneous processors. Also, there are architectures like the ARM Big Little, which has this built into it. It has two Cortex A15 cores and two or more Cortex-A7 cores, and they have exactly the same instruction set architecture, but totally different performance characteristics. Composability means that you should be able to write a library, a function or something callable from another parallel part of the program. And this is not the case if you program with explicit threading and so on. So task parallel programming leads to composable programs. You have the opportunity to write functions or reusable parallel components that others can use in their parallel code. So tasks are the greatest things in sliced bread, right? Well, not quite. So far, debuggers mostly do not yet understand tasks. Operating systems definitely do not understand tasks. They do not know if a program has enough tasks to execute well. They don't know if a program needs more threads to actually execute more tasks and so on. They just take the number of threads asked for and schedule them on the cores. And also other layers of the software stack like hypervisors and so on do not understand tasks. In a way, it's a great moment for or opportunity for innovation and some nice research to be done. So to conclude about tasks, task parallelism is an important programming model for multi-core computers. The program structure remains close to the sequential. The execution order on one processor is identical to sequential, which is very good for debugging. There is no need for other synchronization methods beyond sync. We can effectively deal with performance heterogeneity. We have Wool, which is demonstrated to be a portable and very efficient implementation, lower overheads than any other implementation of task parallelism, and already works on many architectures and more operating systems on the way. Go to the website and follow instructions on how to do a quiz. And finally, there is a hands-on on task-centric programming you can do. Go to the website, find out how to download the code for the hands-on exercises. I recommend that you do it in these manners. There is a subdirectory called Recursive and Compare, which has the same program implemented in 3 task parallel models. It has OpenMP, it has Silk, and TVB. OpenMP, you control the number of threads with the environment variable OMP num threads. With Silk, you have to specify this environment variable. With TBB, the program is actually set to read the OMP num threads variable, so you do the same thing as with OpenMP. So look at these examples. See how the same program is implemented in 3 different ways. Try them out, see if there are performance differences, and try to figure out why and so on. Then you should parallelize the quicksort program, use OpenMP, Silk, and compare performance. You can go back to previous codes you've done and replace OpenMP for loops with the Silk for, which is a way to parallelize for loops using tasks. And if you need documentation, here's the link to it. Thank you.